Okay, in this video, we are going to talk about Routh criterion or Routh table here and why we need to use Routh table in order to investigate the stability of the control system. Actually, this method is one of the methods used to investigate the system stability or study the system stability. We are going later on. We are going to learn several methods to apply or to be used to analyze the stability of the control system, either in chapter 5 using root locus, or then we are going to use the frequency method using the body plot and so on. Okay. So in this part, we focus more on the using Routh table to analyze the system stability and to identify if our control system is stable or not. Why we need to use it? Because actually it's not easy to find the location or to identify or locate the location of the poles either on the left side or on the right side of the S-plane, so we can decide the system is stable or not, especially if you have a system with higher order. So I mean, if you have system with the root or the characteristic equation, which is simple, like mean to the highest degree of 2, so like s square plus 3s plus 2. So this is the characteristic equation. If this one is the characteristic equation of your system, so it's easy, just you make it equal to 0, then you find the roots for this equation, so you can find the solution for this equation, which will be s plus 2, for example, times s plus 1 equal to 0. So this will give you s equal to negative 2, s equal to negative 1. So it's easy to decide that your system is stable because the poles are negative and located on the left half plane. So no poles on the right side, so no positive poles, so your system is stable. So if your characteristic equation is like this one, so it's easy to apply. But assume that you have the characteristic equation is like this one: s to the power of 5 plus 3 s to the power of 4 plus 2 s to s cubic plus s square plus 5s plus 10 equal to 0. So if your characteristic equation like this one, it's not easy. We will have actually 5 solutions, because to the power of 5, that means we have 5 solutions for s. We should have S0, S1, S2, S3, S4, S5. Each value of S is not easy to be calculated or solved similar to this method. So in this case, we are not be able to find the location of the poles. If we are not able to find the location of the poles, we are not be able to identify if our system is stable or not. For that reason, we are going to use the Routh criterion here, and we are going to build or generate Routh table in order to identify the location of the pole. Is it on the left half plane or on the right half plane? If it's on the left, we say the system stable. On the right, we say the system unstable. Okay. So before we go to find or to generate the Routh table, we need to know or we need to confirm that the sign of all coefficients for the characteristic equation are the same. So for example, here this sign is positive, that one is positive, 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 positive. So all signs are positive or all signs are negative. In both cases, we can apply or generate Routh table. Otherwise, no need to generate Routh table because our system will be unstable. Okay. So I mean, we cannot apply the Routh table method in that case. Okay. So the method here for Routh table requires two steps. The first, you need to generate the data table. We call it Routh table. Okay, this is the first step. We have two steps. First, you generate the Routh table. Then you interpret the Routh table and to see for the closed loop. Actually, we mentioned before we must use the closed loop transfer function, not the open loop. So we are going to interpret the sign of the coefficient of the whole pools, or the whole coefficient. So if there is no change in the sign, that means all our pools will be on the left side. If there is at least one change in the sign, that means there is one pool on the right side, so the system is unstable. Okay, so the first you need to confirm that the coefficient all have the same sign, either positive or negative. This is the first step. Then you generate the Routh table. After you generate the Routh table, we are going to see how to generate the Routh table. Then we are going to check the sign of the coefficient in the first column of the Routh table. If there is no change, then the system is stable. If there is one change at least, so the system is unstable. Okay. So this is how to generate the or construct the Routh table. So the first you need to have the TS or the closed loop transfer function. This is the closed loop transfer function actually, not open loop. Please, this is the closed loop. Don't or never use the open loop transfer function for Routh table. Closed loop transfer function. Okay. So when you have the closed loop transfer function, don't look at the numerator. This part no need to see. Just focus on the characteristic equation or the denominator of the transfer function. Okay, then you see what is the highest degree of S here. It is 4. Okay, so you are going to start your Routh table from the highest degree, which is 4, until 0. You are going to build the first column in your Routh table here. This is the Routh table actually. Routh table, you are going in the first column of Routh table, you are going to write S from the highest degree or highest order to the lowest. We start S4, so we are going to write S4, S3, S2, S1, S0. We start S5, we are going to write S5, S4, S3, S0. We start S3, so S3, S2, S1, S0, and so on. Okay. The second step, after you write the first column here, you are going to identify the coefficient for each s. Okay, the coefficient for each s represent the number or variable here before the s. Okay, so for example, for s4 it is a4, for s3 it is a3. In this equation example actually a2, a1, and a0. Okay, so these variables or this coefficient will be listed in the first and second row of your Routh table. So we just put it a4, a2, a0. This will be because we start from even number, so we take the even number. So 4, 2, 0. Don't say 4, 3. No, even number 4, 2, 0. Then 3, 1, 0. Why 4? Because we are in the line of S4. 3, we are in the line of S3. If it starts from 3, so we are going to say A3, A1, A0, and so on. Okay. Then A2 and A0. So we just list the coefficient as it is. No need to do anything. In the first line here, first row and the second row, we just list our coefficient that is existing in the characteristic equation. The next step or the rest of the Routh table will be generated based on a specific equation or based on the specific definition for the variables. So the first column here, we are going to call this one B1, for example, just to identify or to define, because we are not using numbers here. We are going to see later on some example which use number. Here we use variable just to make the general form of the Routh table. Okay. So what this element represent, which is B1 here, B1 actually represent the determinant of 2 times 2 determinant, which is represent from the first row, I mean the first column is the 2 elements here, which is A4, A3. This is the first column. The second column represent the next elements. Okay, so you just put A4, A3, A2, A1. It's like you put like determinant on these two columns. Then you add negative, sign negative. This is actually formula you need to follow. Don't no need to think about it. Just put the formula as it is. Negative A4, A2, A3, A1. Okay. Then on the denominator of B1 here, we are going to put A3, which is this element, the element which is placed on this area, which is the second row of the first column. The second row of the first column. Okay, this is for B1. We go for B2. We use the same. This A4, A3, A4, A3 here. Okay, we just uh, use highlighter here. So you can see here this is A4, A3. It is the same like this one, A4, A3. It is the same as A4, A3, A4, A3. So this, the first column is used for the old coefficient in that in this line. Okay, the second one here represent the second element, which is A2, A1, then A2, A1, but this will be changed for the second one. This will be the second element. So what's the second after A2, A1? We have A0 and 0. So this will be A0 and 0. For the last one, no more column, so we put it just 0, 0. This is how to generate the coefficient for the S square. We said the first two, we just take them directly from the equation or from characteristic equation. Then we start to generate it them by using this formula. You can see also here A3, 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 A3. So this will be the coefficient of the second row in the first column. Just put it here. So we open this determinant. It will be like A4 times A1 minus A2 times A3. We find the values. We put it to represent the value of B1. Then we open this one to represent the value of B2. We open that one, which is already 0. Because A4 times 0 minus 0 times A3, it gives you 0. We go to the next S here to fill up. We need to construct the whole rows and whole columns for the Routh table. So we call this one is C1, and C1 will be the previous two or the first column will be the previous two lines. You see, the first line here will be A3, the second will be B1. So A3 B1. So A3 B1. This will be common for all A3 B1, A3 B1. Okay, and the denominator will be the second element here, which is b1. So a3 b1, so it will be b1 b1 b1. So this will be the second element. The only change will be on this the second column. So the second column here for the first line a3 b1, this is the first line. The second will be a1 b2. So we just put a1 b2. This will be the second column. For that one, the second column will be the next one, which is 0 and 0. The third one, 0 and 0, because no more, all 0. So we can see here, start to go 0. This one it will be 0. This one we call it C1. We go to the next. It will take the first column will be the common elements here, or the first element, which is B1 C1. So we bought B1 C1, B1 C1, B1 C1. The second one will be the second column, which is B20 for the first line, B20. For the second one will be 0, 0, 0, 0. Okay, so we just put 0, 0, 0, 0. Don't forget to put the sign negative here for all negative, negative, negative. Okay, and the C1 here represents, we said B1 C1, so the denominator will be C1 for all, which will be the second element. This is how to generate or how to construct timetable. I mean Routh table. So when we construct the Routh table here, we find the value of B1, the value of C1, B2, and D1 also. So all the elements are there. Then we are going to decide, is our system stable or not? How? We will interpret the sign of the first column elements. So for example, if A4 here is positive, A3 is positive, P1 is positive, C1 is positive, D1 is positive, so we are going to say our system is stable. Why? Because all the elements in the first column, they have the same sign. If all are negative also, we will say the system is stable because no change in the sign. But if one of them is negative, so we have changed from positive to negative, negative to positive again. So that means we have one or two change. So if you have one change or two change, In this case, you are going to say your system is unstable. Whatever is the value of the pool, no need to calculate the value of pools. Is it 5, 2, 3, 10, 100,000? No need. Just need to know the value of the sign of the variable. Is it positive or negative? If there is change or there is no change. We're going to take example here. So in the example, it's become more clearer because we are going to use the numbers instead of using variables. So the question said, or the example said, make Routh table for the system in the figure A here. This is the system. Actually, this system consists from GS with the feedback. So this one is a open loop transfer function, and the open loop transfer function here cannot be used directly to generate the Routh table. This is the open loop. This is GS actually. It's not TS. This one is GS. Okay. So the GS cannot be used directly to generate the Routh table. We need to find the value of TS, which is here. After we find TS, that means we are going to consider the feedback here. We say TS will equal to GS over 1 plus GS. Why plus GS? Because HS equal to 1, so no need to highlight anymore. HS here is HS equal to 1, correct? So no need to highlight. We're going to use positive because we have here negative value. If it's negative, if this one is positive, this become negative. So you please refer to chapter 3, the transfer function of the feedback system, which is the third configuration. We highlighted 3 type of configuration, which is cascade, parallel, and feedback. You go to the feedback, you see how we calculate this closed loop transfer function for the feedback. Okay. So now TS equal to GS over 1 plus GS. You just substitute for the value of GS, which is 1000 over S plus 2, S plus 3, S plus 5. Substitute here, substitute there, and simplify. You will get this transfer function. So this transfer function comes from this equation. Okay. You substitute GS in this equation, you got this one 1000. So it's easy. Just put the gain, which is 1000. You can see here. If you have a unity feedback, this we call it unity feedback because HS is equal to 1, so we call it unity feedback. So you just put the gain there and you open the bracket. So S times S times S give you S cubic. S times 5, it will be 5S squared. 2 times S, so it will be 2S squared, and so on. So just open this one, you simplify, you go to S cubic, 10S squared, 31S plus 1030. Okay, and this one represent the characteristic equation. This will be the characteristic equation of your system. So how we can apply Routh table? You need to use this equation, make it equal to 0, then you find the roots or the value of the pools here. In order to find the value of pool, just generate the Routh table instead of find the value of pools. So the third order equation is not easy. Just go apply Routh table. Build the Routh table. From the Routh table, we can decide is our system stable or not. Because the question here is to make the Routh table. Then from the Routh table, we can decide is our system stable or not. Before that, I told you before, we need to identify the coefficient of the characteristic equation S values here. Is it all the same sign? If yes, so you can build the Routh table and study the performance, I mean the stability. Okay, so this one is positive, 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 positive. So all positive, so they have the same sign. So they said the same sign, the bus or the system bus or the Routh table here, the test of the Routh table, so we can build the Routh table or the Routh array. Okay, what are the steps to build the Routh table? We are going to draw table. The first row represents the value of S, which is S cubic here, S square, S, and S0. We have S from S cubic, the highest one. After that, we are going to list the variables. After we list the variables, we generate the rest of the variables for the table. So this is how we build the Routh table. The first column represents the value of S only, from the highest to the lowest, S cubic, S square, S1, and S0. Okay. Then the first two rows represent the values of the coefficient for S. So if you can see here, what is the coefficient of what's the coefficient of S cubic here? It is 1. This coefficient is 1. This coefficient is 10. That coefficient is 31, and that one is 10, 30. Okay, so this coefficient will be listed in the first and the second row of Routh table. So you have 1, you have 31, then the third one is 0 because we do not have. This one is the coefficient of a, it's like a3, then you have a1, and here no more, is 0. Okay, then the second one will be a2, which is the coefficient of s square, which is 10. Then we have a0, which is the coefficient of s to the power of 0, which is 1030. Then no more here is 0. So this line or this two row is generated from the existing variables. Why we bought here 10, then we bought it 1? Just to simplify our calculation, because if you bought a big number, so when you do the calculation to open the determinants, it become a little bit complicated. So it's easier if you have any common element within the same row, you just divide. It's like in the matrix, if you divide all rows I mean element in the row over the same parameter, it will not affect the value of the metric. Okay, so here we divide, since we have 10 and 1030, we divide over 10. So the first one divide over 10, it gives you 1. The second one divide over 10, it gives you 103. Just to simplification, 0 over 10, it will still also 0. The third step or the third row here, we are going to apply the same parameters or the same equation that we used before here, which is this one, a4, a2, a3, a1. In this case, we have a3, a0, and I mean a2 and a3, a1, a0, and a1. Just apply to the second. So you can see here, the first column is the common one between all the row elements, so it is 1 1, which represent the first column here, a3 a2. 1 1 is a3 a2, so this is like a3 a2. Okay, which is 1 1. Okay, then you put it here, 1 1 in the first column. All in the first column will be 1 1. Also this is 1 1. Okay, this is 1. It's not 0. I can just correct. Okay, so the first element is 1 1. We bought it 1 1 1 1 1 1. It is the common. The denominator is represent the a2. We said it is the second one, so it is a2 here, which is 1. So this, the denominator is 1 1 1. It is also the same. Then we have the value of or the sign is negative for all. The second line represent, or the second column represent the second column here. So the second column for the first element is this a3 a2. The second will be a1 a0 or 31 103. Okay, we bought 31 103. The second element for this line, which will be the next one, which is 0 0. We just put 0 0 here. The second here will be also 0 0 because no more here elements, so we just put 0 0. So now open this determinant. So it's become 1 times 103 minus 1 times 31 over 1, all negative. So it will give you negative 72. Okay. So this is negative 72. Then we have for this one, 1 times 0 minus 0 times 1. So it will give you 0. So the second element is 0. The third element also 1 times 0 minus 1 times 0 over 1. So all give you 0. Now I go to generate the next or the last element here. So the last element also represent the same. The previous two row represent the first column. So it will be like 1 and negative 72. So you just put 1 negative 72, 1 negative 72, 1 negative 72 for all elements. Negative all negatives. The determinant will be the value of the second element here in the row. So it will be negative 72, negative 72, negative 72. please consider the value here negative or positive, because if you have negative over negative, it will give you positive for the last element. Okay, then you have 103 0. This represent the 103 here, and the 0 is here. This for the second row. For the second row here will be 0 and 0, so you just put 0 and 0, 0 and 0. So the value of the variables will be 0, 0, and will be 103. Okay, so these are the two this is the Routh table for our characteristic equation. So you can see here the elements of this Routh table are as follows: 1, 1, negative 72, 103. Here we have 31, 103, 0, 0. Here we have 0, 0, 0, 0. So this will represent the Routh table elements. Okay. So now we generate Routh table. From this Routh table, we can decide is our system stable or not. How? We need to monitor the sign of the elements in the first column. So the first column here, our first column is, we said it is 1, 1, and negative 73 and 103. So if you check the four elements, the sign of the four elements, the first is positive, the second is positive, okay, the third is negative, the fourth is positive. So do we have change in the sign? Yes. From positive to positive, no change. From positive to negative, there is one change. From negative to positive, again we have another change. So 1 plus 1, we have to change. From positive to negative, from positive 1 to negative 73, 73, 72, from negative 72 to positive 103. So we have two change. That means we have two poles on the right half plane. Okay, if you have two poles on the right half plane, that means you have two poles in this area. If you have two poles here, anywhere, I don't know where, but there is two poles on this right side, that means our system is unstable. Okay, the number of roots of polynomial here that are in the right half plane is equal to the number of sign change. So how many change we have? We have two change. We have from positive to negative 72, from negative to positive 103. So this one change, this is another change. So we have two change. That means we have two poles on the right half plane. Since we have two poles on the right half plane, that means your system is unstable. I hope it's clear how to generate a Routh table and how to decide if this Routh table or if this system is stable or not based on the number of change in the sign for the Routh table elements. Okay. Actually, we have two special case. When we say special case, that means it's abnormal. So we cannot decide is our system stable or not. Why we cannot decide? Because we said we are counting the values or the number of change on the in the sign from positive to negative or from negative to positive, and this is applicable only for the real I mean for the integer numbers, I mean numbers which is either positive or negative. As we know here, this is our line, so the positive numbers will be on the right and the negative number will be on the left. But how about the value of 0? If you have 0 in the first column, actually we said we are using the first column of Routh table to decide if the system stable or not. If you have one element is 0, so for example the element are 2, 5, 0, 3, 7. Okay, now if I ask you now how many change in the sign from positive to negative, from negative to positive, you cannot answer because you have 0 here. So 0 is not a positive number, 0 is not a negative number, 0 is 0. So in order to decide if the system is stable or not, we cannot decide since we have a 0 in the first column of the Routh table. So for this, we say this there is special cases. So special cases, that means you have 0 in the first column. In this case, you need to have some special techniques in order to understand or to investigate or identify the stability of your system. So the two cases that we have, the first case, we have only 1 0 in the first column. So if you have 1 0, that means the others are not 0. Here we have, for example, 2 and then 0. Here we have 3, 2, 5, 0, 9, 7, 0, for example, 0 and 0. Okay, so the first case that you have 1 0 in the first column only, and this the only there is 0 only in the first column. So you have 1 0 in the first column while the others are not 0 here. This is not 0. Okay, or the second case, the entire row is 0. That means instead of have 2 here, you have 0, 0, 0. So the whole row here is 0. You can see this row all equal to 0. If the whole row equal to 0, this will not allow you to complete the calculation of the Routh table because all these values become 0, 0, 0, 0, 0, 0. This is the case if you have entire row of zeros. Okay, so these are the two cases you need to consider while constructing your Routh table, and in this case you have to solve the or to complete or construct the Routh table in a different way. Okay, so we will see an example here. This is the first example on the case that you have 1 0 on the first column of the Routh table. Okay, so we have a 0 here, and this 0 actually will not allow us to determine if our system is stable or not, because we cannot say 2 to 0 is positive. No, we cannot say 0 to this value is negative. Okay, so we cannot decide. So in this case we need to identify or to deal with the Routh table in a different way. Okay, so we are going to see here how to construct the table when we have a 0 in the first column. So actually for this case, we have two solutions or two methods to solve. If you have a 0 in the first column of Routh table, so you have two ways to solve this issue, two ways to overcome this problem. Okay, the first way is, as we can see in this slide, we assume this 0 is a small value, we call it epsilon. We assume it's epsilon, and the epsilon is a very, very small value close to 0. We don't know close to 0 from the left side or from the right side. It can be 0.00001, for example, or it can be negative 0.0001. It can be positive or negative, but close to 0, and we don't know is it on the left or on the right. Okay, so if it's not a 0, so that means we can decide is it positive or negative by using some assumptions here. Okay, so how we can build a Routh table for this closed loop transfer function? Already gave you the closed loop transfer function and already gave you the characteristic equation here: s5 to s4, 3s cubic, 6s squared, 5s plus 3. So we just list the value of s from the highest to the lowest as usual in the first column, s5, 4, 3, 2, 1, 0. Then we are going to list the variable or the coefficient of s on the first two rows. So the coefficient of s5 is the first row will be for the odd, because the highest is odd. So the odd numbers, then the even numbers. Okay, so the odd number, that means the highest 5, 3, 1. This is the odd. The even will be 4, 2, 0. Okay, so that is the coefficient for 5, it's 1. The coefficient for 3 is 3. The coefficient for 1 is 5. Okay, so this is the coefficient 5, 3, 1. These are the coefficient for the odd numbers or the odd degree or the odd order of the s. Then the coefficient of the even numbers is 2 for 4, 6 for 2 square, and 3 for 0. So we put 2, 6, 3. Okay, now we complete construct the rest of elements. So if we have this element here, how we got it is 0, because we said the first element represent what? It will represent the first column, which is 1, 2, the previous two elements, which is 1, 2, and the second will be the second element, which is 3, 6. So 3, 6, and this will be negative based on our equation, and we will divide on the second element, which is 2. So if you open this one, 1 times 6 minus 2 times 3, it will be 6 minus 6 equal to 0. So we got this value is 0. Okay, so this is how we got this value. Actually, we need to go back to the previous example to see how we calculate this element, which is 0, 7 over 2. For the 7 over 2, it will be like this one. Actually, its original value was negative 1, 2, is the same as 1, 2 here, and the second element is 5, 3. Then this determinant over the element, which is 2. Okay, so 1 times 3 is 3, minus 5 times 2 is 10. 3 minus 10 is equal to 7. 7 with the negative here, which become negative 7. I mean positive 7, because we have negative times negative 7. 3 minus 10 is minus negative 7. Negative 7 times negative, it will be positive 7, and 2 here. So we have 7 over 2. Okay, so the rest also the same. It will be 1, 2, and 0, 0. So it will give you the value of 0. Okay, now we do not have row of zeros. We only have one value in the first column, which is 0, while the second, it's the value 7 over 2. So we are going to deal with the first case. The first case, if you have only 1 0 in the first line, you stop here. Don't continue to calculate. Don't calculate the rest. Just stop. When you meet the 0, you check, is it the 0 in the first row only, or in the whole or entire row? I mean in the first column or in the entire row. So if it's in the first column, you just assume the 0 equal to epsilon value. We don't know the value of epsilon. Then this epsilon will be used to calculate the rest of the Routh table. So in the first is epsilon. If you want to calculate the second, it will be like 2, the determinant for the second this how we got this value here. Actually, this value is come from, we have the determinant, negative determinant, the previous 2, then we have epsilon, then we have 6 and 7 over 2 over epsilon. So you solve this one, it will be 2 times 7.2, so it will be like 7 minus, will be 7 here, negative 7 minus 6 epsilon over epsilon. So we got this equation, 6 epsilon minus 7 over epsilon. You just open this, negative 7 become negative 7, negative times negative become positive 6 epsilon. So we got 6 epsilon minus 7 over epsilon. Okay, so and you calculate the rest also for this one and that one by using the formula of the this one, a for a3, this one also you substitute for the value for the next one, and so on. You refer to the previous examples to see how we calculate this, the rest of Routh table. Our focus here is how to solve the issue of existence of 0 in the first column. So now we substitute by epsilon only, then we construct the calculation. Now this will be our generated first column of the Routh table. It will be 1, 2, epsilon, the one that we use to replace 0, 6, 6 epsilon minus 7 over epsilon, the one that we calculate here, then the rest also we calculate. If you go for the first column here, we want to check, is our system stable or not? We want to check how many change in the sign of the system in the sign of the system coefficient, okay, or element in the first column. So 1 to 2, positive to positive, no change. 2 to epsilon, we don't know, is it positive or negative? It depends on our assumption. If we assume epsilon is a positive number, or we assume epsilon as a negative number. We said epsilon is very small, so it's 0.0001 or 0.0005. Okay, is it positive or negative? Depends. Okay, so we are going to draw or to write our sign here. So the first 1 to 2, 1 is positive, 2 is positive, and in this column we assume that epsilon is positive. So if epsilon is positive, so it becomes positive here, correct, based on our assumption. Okay, if epsilon is positive, the next one here, if this value is positive times 6, so it will give you a value. But this value, since epsilon is very small, try to multiply 6 times 0.00001. Okay, for example, so it will give you a very small value. So this value becomes small, and here we have a negative value. Negative 7 become much higher than 6 epsilon. So the numerator in this case become negative, and the positive here, the epsilon in the numerator or in the denominator is still positive, correct? We assume it's positive. So you have negative 7 over positive, so it will give you the sign is negative in this case. Try to multiply epsilon by or 6 times 0.0001, for example. You will get a very small value. If this value is small, this become negative 7, so the negative 7 become higher, so the numerator become a negative value. Negative value, the denominator is positive. Why? Because we said here it's positive, so negative over positive will give you a negative value. Okay, we go to the next one. 42 epsilon minus 49. We said this one we calculate by assuming this value, epsilon 6 epsilon minus 7 over epsilon. This is the first column. The second column will be 7 over 2 and 3. Then we open the determinant, we got this equation or this value. Okay, so now since we assume epsilon is positive in this case, so 42 epsilon will be positive because epsilon is positive times 42, it will be positive. 49 here is negative, but 42 is positive. Here it becomes small value, but still also positive. 6 epsilon square is a negative, so this become for sure our determinant will become a negative value. Why? I mean the numerator here will be a negative value. Why numerator is negative? Because we have negative 49, we have negative 6 times epsilon square, so all this become a negative. The numerator become a negative value, whatever is the value, okay, but it is a negative. Then how about the denominator here? This is positive times 12, small value times 12, and negative 14. For sure negative 14 is greater than 12 epsilon. Why? Because epsilon is very small, so we have a negative 14. That means the denominator also is a negative value. If the numerator negative, denominator negative, so negative over negative will give you a positive sign. Whatever is the value, we are not going to calculate the value here. Our focus only on the sign of the element. Is it positive or negative? Okay, then we have the 3, it has a positive value. Okay, now this is in the case we assume epsilon is positive. You can see here how many change if epsilon is positive. Positive to positive, no change. Positive to positive, no change. Positive to negative, there is one change. Negative to positive, there is another change. So we have to change. That means we have to change. There is two changes, and these two changes, that means two poles on the right half plane. So in this case, our system is unstable because we have two poles on the right half plane. Okay, the next case, if we assume the value of epsilon actually is a negative value, that means it is it's negative 0.0001, so it is close to 0 and it is a negative. Okay, so the first case, 1 is positive, no change. 2 is positive, no change. Epsilon value will be negative because we assume it is negative, so we put it negative. Now if we put epsilon is negative here and this value is negative, 6 times epsilon, it will be negative because we have a negative value and we have negative sign, so this the numerator will be negative, and we assume the epsilon is negative itself, so also the denominator will be negative. So we have negative over negative, it will be a positive value, so it gives you a positive value here. So then next, if we substitute for negative value for here epsilon, so 42 negative, so it will be for sure is negative, 49 is negative, 6 epsilon square is it will be positive epsilon here, but we have here negative also. So the numerator will be for sure negative. Then if epsilon also is negative, so the 12 time epsilon will give you a negative value here. Here we have a negative, so for sure it is a negative. So negative over negative will give you a positive value. Whatever is the value, we don't care. Okay. Then the last one, 3 is a positive value, just leave it as positive. Now we check the second case. How many change do we have? We have positive to positive, no change. Positive to negative, it is one change. Negative to positive is another change. Positive, 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 no change. So we have two changes. So we have two poles on the negative on the right half plane. So our system is unstable because we have two roots on the positive side or the left right side of the S plane. Okay. So see here how we solve the issue of 0 in the first column. We have the first column, we have value of 0. We assume the 0 is epsilon, and which is a small value close to 0. We don't know. It can be positive value. So in this case, we can find the sign change, and we find there is two change. Also, it can be negative value. Also, as we find two change. So in both cases, it is the same. It gives you the same result. Either it is positive value or negative value. So we can identify the stability of the system. So this is the first case, which is 1 0 in the first column. Also, this is the first method to solve this issue. There is another method to solve the same problem, which is the zero, the existence of 0 in the first column only. So this method, it's easier, and we can see here in this slide how we solve the issue of existing of 0 by using the second method. So we call it the reverse coefficient method. Reverse coefficient means instead of use the existing order of coefficient, which is 5, 4, 3, 2, 1, we are going to reverse this equation. Why? To avoid obtain the value of 0 in the first column. This is the same equation actually, the same transfer function that we see here, s5, 2s4, 3s square, 6s square, 5s plus 3, same, s5, 2s4, 3s square cubic, 6s square, 5s. It is the same example actually. If we use the Routh table, for sure we are going to get the 0 in the first column. If we use it directly, we are going to have the 0 in the first column, and we need to apply the epsilon assumption, okay, in order to identify the system stability. So in the other method to solve, we can reverse the coefficient for the s values. So you can see here, actually we have the coefficient for s5, for example. The coefficient for s5 in this equation, in the characteristic equation, the coefficient is 1, correct? And the coefficient of s0 is 3. The coefficient of s1 is 5. The coefficient of s squared is 6. The coefficient of s cubic is 3. The coefficient of s4 is 2, correct? So this is the original one. The left one, on we put the left, which is the coefficient of s0 to be the coefficient of s5, okay? And we put the coefficient of s5 to be the coefficient of s0, okay? So as you can see here in our equation, s5, the coefficient for s5 is 3. The original was 1, but in this equation it's become 3. Why? From where we bring the 3? This one. So we take for s1, put it for s5. We take for for s0, we put it for s5. For s1, we put it for s4, which is 5. This one is become here. Then for s square, we put it for s3. It's become 6 here. For s3 become for s square, which is 3. for S4 become for S, which is 2, and for S5 become for S0, which become 1. Okay, so this we call it the reverse. You can see here reverse coefficient. That means we take the coefficient for the highest order to the lowest, and from the lowest order to the highest. Okay, so these are the values for our system, or the coefficient for the new order for the coefficient, and this can be used with our Routh table here, the new Routh table. So what we are going to do, we draw the Routh table S5 until S0. We are going to use the new coefficient. So the coefficient for S5 is 3, for S3 is 6, for S1 is 2, 3, 6, and 2. Then the second line become for the even number, so the S4 is become 5, the S square become 3, and the S0 become 1. So we write the coefficient, then we complete to find the elements. When we find the elements or the rest of the coefficient here for this column, we are not going to find 0 here. No 0, no more 0, it's 4.2. No more 0, it's 1.3. No more 0, it's 1.75 and 1. Okay, so by reverse the coefficient here, we got a new values which is not include the 0. So we solve or we overcome the problem of 0. So it's easy for us now from this Routh table to decide is our system is stable or not. So we see the sign here. So from 3 to 5, 3 is positive, so this one is positive. Actually we can highlight here. So the one is positive, the first element is positive, the second element is positive, the third element is positive, this one is positive, this one is negative, so this one is positive. So how many change? We have one change from positive to negative, so this is 1, and we have one change from negative to positive again, which is 1. So we have two change, that means two poles on the half or the right half plane. Okay, so since you have two poles on the right half plane, so your system is unstable, and this one what we already got from the previous method. Okay, so it doesn't mean the method will not change. The method will not change the status of the system stability. The system is unstable. Either you use the first method, you use the second method, you assume the coefficient is or the epsilon is positive, you assume the epsilon is negative. In all cases, since your system is the same, so the status of system stability also still the same, which is unstable, and it has two poles on the right half or in the right half pole. Okay,